Thank you for watching, liking, commenting, sharing, and subscribing right now.
So last year, we reached out to a handful of people at UW to see what they were up to, and made some different connections, including through Christine Peterson, who inadvertently connected me to Firas. And I didn't realize that some of the projects that I had featured myself, either in videos or on Twitter, were actually started here in the Seattle area, certainly the University of Washington. And keeping in the thread of science, technology, how it impacts our lives, I thought it was always interesting to look at certain projects that would allow people who don't know much about science but are always in awe of how it works to be able to play along at home. So without further ado, the Fold It project with Firas Khatib.
Thank you. So I work in David Baker's lab at the University of Washington, and the Baker lab is kind of most known for the protein structure prediction algorithm, which is called Rosetta. And in collaboration with the Department of Computer Science and Engineering at UW, we've developed this free online protein folding video game that I will start off just by showing you. And so, so this is Fold It, and what you have here is a protein, and you have a scoreboard up here with your score and a leaderboard, and you have all these tools that you can use. You can shake the side chains, and so here the side chains are shaking. You can, and you have sound, and you can wiggle the protein. And if you do well, you rank up, which is lovely. So this is compared to the other players. And so you can do all sorts of things. You can pull the protein apart, and these red spheres indicate voids. These ones indicate clashes. And we also have intro levels to try to teach, or you can rank down if you do that, to try to teach people first of all about proteins and how to play with them. And so with these intro levels, you kind of have a tutorial telling you what you need to do. So this is a hydrogen bond, and you want to align sheets to create them. And so you try to do this by bringing this over here, and you can see your score changes in real time, and this is using Rosetta's energy function. And so great hydrogen bonding. So then if you shake the side chains a bit, your score goes up, and maybe if you just do a little wiggle, hooray! And so then you can go on to the next level. And I'll just do one more example here. So this is telling you match up the donors and the acceptors. You can connect them with rubber bands, and so put in these rubber bands, and then the rubber bands pull the protein together when you wiggle. And you hear these poppings. Those are the voids that are popping. So you're getting rid of voids, which is a good thing. And your score goes up, and then if you do well, you get the nice music and all that. So that's Fold It. And so the question arises, why proteins? How come they get their own video game? What's up with that? So proteins are actually involved in almost every process that's going on in your body. Right now, proteins are breaking down the lunch you just ate, and hopefully proteins are sending signals to your brain from keeping you from falling asleep right now because of food coma. But the problem is that proteins are so small that you can't actually see them with a microscope. So here are actually different representations of the same protein, and you saw in Fold It we use kind of a cartoon-like representation with side chains. And so why is protein folding important? Well, the three-dimensional structure of a protein determines the function of that protein. And so many diseases are believed to be the result of misfolded proteins. So Alzheimer's, cystic fibrosis, Huntington's, various cancers, Creutzfeldt-Jakob's disease. There's one class of proteins that are called the prion proteins, and these are these horrible brain disorders that are just caused by the misfolded form of the normal prion protein. And so by being able to correctly determine the structure of these proteins, we can better understand their function and how we can target them with drugs. So that's why protein folding is important. So now, it's actually possible to solve protein structures, certain proteins, experimentally. The problem is it's very, very expensive and extremely time-consuming. So what I'm showing you here is every year these blue bar graphs are the number of proteins that have been solved experimentally. And so in May of 2008, the total was about 50,000. But if you compare this to the number of protein sequences that have been solved, especially since the Human Genome Project was solved and all the other genomes that are being solved now, you can see there's this very, very big gap between the number of solved protein structures that we have and the number of protein sequences. And so what we're trying to do in the protein structure prediction community is to bridge this gap using computers. And so the protein folding problem is just very simply, you're given a protein sequence, which is just a bunch of letters, there are 20 different amino acids, and you want to determine the three-dimensional fold of that protein just given the sequence. And so the way we do this is by using the fact that the native or correct-like fold of a protein is going to have the lowest energy. So, for example, if this is showing you the energy landscape of a protein, this would be the unfolded state up here with a very high energy, so kind of flopping about, and as it's trying to fold, it's going to have these low energy states and possibly even these higher energy states, but the actual correct fold of that protein, the native state, is going to have the lowest free energy. And so on the right, what I'm showing you is an energy funnel, and this is, I'm going to be showing these types of graphs a lot, and so what it is on the x-axis is the distance that the protein is from the native structure, and on the y-axis is the free energy. And so all of these black dots are actually computer simulations by Rosetta for a given protein. So, for example, this dot here is a prediction that has, medium high energy, but is very, very far from the correct topology. And so, in a good case, so this is a good case because the ones that are closest to the native state actually have the lowest energy. So, unfortunately, we don't know when we're predicting the structure of a protein that is unsolved. We don't know how far it is from the native state, but if the one that has the lowest energy, the lowest Rosetta energy, is the closest one to the native, then that's a good thing. So what we hope for when we have these clouds of dots representing computer simulations is that the one with the lowest energy is the closest to the native. So how does Rosetta work? Essentially, we kind of cheat. We use short fragments of known solved structures when we do our predictions. So if we're given a long sequence that we're trying to fold up, we just break it down into very small pieces and look at all the solved structures in the protein database, and basically we just try to fit them all on and see how they go. So I'm going to show you a little movie of Rosetta. So this is basically starting in an extended conformation, and then by using fragments of known structure and basically trying them all out very, very fast, one at a time, and seeing which ones fit, which ones clash, and which ones give you a better energy. Rosetta basically tries to fold up a protein in this way, and trying also to promote long-range interactions between these strands here. So of course I'm only showing you the nice case. And so what you end up with when it stops flapping about is a conformation that's pretty close to the native one, which is shown here in gray. This is ubiquitin. And so from this low resolution model, we then do a high resolution refinement where we put on all the side chains, which you kind of saw in the game, and then we basically just wiggle it a bit. And so the backbone here doesn't move much, but these side chains are basically trying to remove clashes and trying to fill voids in the core. So we're actually very lucky in the field of protein structure prediction because we have this thing called the CASP experiment. And the CASP experiment is it's this double-blind experiment that's held every 2 years where experimentalists that are about to solve the structure of a protein, but they haven't solved it yet, they release that sequence to the rest of the world. And all the labs around the world try to predict how that protein is going to fold up, but it's unknown. So there's absolutely no way anybody could cheat. And so at the end of the summer, all the predictions are in, and there's this big meeting at the end of the year where we find out which protein structure prediction methods did the best. And this is held every 2 years, and you basically get to see which methods are performing well and what we can do to improve it. And so one of the big things at CASP is to have an improvement over the template. And the template is just, in cases where there's a solved protein that's actually very similar in sequence to the one that we're trying to solve, we use that structure as a template, kind of as a starting point. And so you would think that if you're using a solved structure as a starting point to predict your protein, that you would actually, maybe do better. You wouldn't make things worse. But actually, unfortunately, in our field, most of the time, so this is from Cas6 in 2004, we make things worse. And so the question is why? Why is protein folding so difficult? Well, the first thing is that there's just so many degrees of freedom. So this is just a small chain with 2 side chains here. And you can see already all the different degrees of freedom. And so proteins have hundreds and sometimes thousands of amino acids. And so with all the computers on Earth, it'd be impossible to simulate just all the different ways that one protein can fold. So that's the first problem. The second is that the energy landscape is just littered with all these local minimums. So you can think of the protein folding problem as you want to find the deepest crater on the moon. And what you have is a bunch of robots with an altimeter and a walkie-talkie. And so you drop all these robots all around the moon and you say, go find me the deepest crater you can find. And so the robots are moving around, and when they get down to a crater with the altimeter, they go, ooh, I found a low point, and they report back with a walkie-talkie, this is the lowest elevation I found. And so you can see that if there's a lot of craters, they're probably going to find the closest crater, and they're not going to want to go back up because they're trying to find the lowest elevation. And so that's one of the big problems. And to make things worse, when you get near the deepest crater on the moon, it's going to be very, very, very narrow. And so you could actually be really, really close, like right here, and you'd be stuck in this crater, and you wouldn't be able to find the actual native one. So what do we do with Rosetta? Well, the protocol that we use is we start with a low resolution model, which is what I showed you earlier, and then we basically try to diversify it as much as we can to try to get out of whatever local minimum that we're trapped in, and then we do a local optimization or wiggling, as you saw, and in hope that at least one of these will get to the native state. And sometimes we're actually very successful. So what I'm showing you here, again, each black dot here is one simulation of Rosetta, and this is the best energy that came out of that simulation. So, for example, this dot way up here had a really, really bad energy and is actually very, very far from the native structure, but that was the best solution that came out from that run. So that was the closest crater that robot found, if you will. And so you can see in this case, we have all these different simulations, and of course, we don't know which one is the closest from the native at the time, but we got very, very lucky in that the lowest energy one right here is actually indeed the closest. And you can see this is a superposition. The native structure is in pink here, and the Rosetta prediction is in blue, and even the side chains here match. And this was a very amazing and kind of like a breakthrough in Cas6. But this is definitely not always the case. So there are many cases where we have all these simulations and all this computing power, and the lowest energy that comes out is this structure way over here, which is very, very, very far from the native solution. And you can see here how these two proteins differ. And so the problem here is a sampling problem. We can't sample enough, and so even the ones here that are very close to the native, this isn't too far, they're just not able to get into this very deep energy funnel. So how can we solve the sampling problem? Well, we could develop smarter algorithms, and I guarantee you we're really working on that very hard. But one of the main things that has been successful is volunteer computing. And so this is where Rosetta at Home came in. And so, as I said before, the biggest supercomputer just isn't enough for us. We need more. And so what we're doing with Rosetta at Home is to try to use everyone's computers, all your computers, and just sample even more, just to get that one dot that's lower and closer to the native. So, for example, if this is your regular Rosetta run in our lab, on our big old cluster, and these are all the conformations that come out, we can give this to Rosetta at home, and we can get so many more data points. And just one is all that we need, but in this case, with Rosetta at home, we were able to get this one prediction here that's the lowest in energy, happens to be very, very close to the native, and you can see here, this is the native structure, and this is the lowest energy prediction. And this was done on Night Lord's computer. They're from the Scottish Boink team. And all Rosetta at home is just a screensaver. I'm sure you've heard of SETI at home. Well, Rosetta at home is very similar for proteins. And so using Rosetta at home, we have over, I think, 1.3 million users right now, probably even more. And using Rosetta at home for CASP, we were actually able to do a lot better in the next CASP, in CAS7. So this is all the Baker Lab submissions for CASP, and you can see a lot more of them were better than the template. There's still a lot of work to be done, but using all this computing power, we were able to do better. And let me show you just a few examples of. So Rosetta is starting with this pink template here, and the prediction is in green. And the native here is in blue. And so for a lot of these cases, you have this, the pink is kind of the starting point, and the green is what Rosetta predicted, which is closer to the native. So this was exciting. And the really cool thing is that the Rosetta at home users just really got into it. They, you have a ranking of how many hours your screensaver has been predicting, how good the structures your computer has been predicting, and some of them even got so into it that they would stare at the screensaver and go, "Oh no, this is folding incorrectly. It's moving the helix here. It really should be over there." You know, people were staring at screensavers, and so this is actually how Foldit got developed. And so one of the other ways we can solve this sampling problem is to use the collective brain power of gamers. And so that's how we began Foldit. And the first lesson that we learned in Foldit is that gamers don't like negative scores. So negative energy, that doesn't work. You have to have a positive score. So the first thing we changed is a score to be positive. And so the question that arises with Foldit is, so are the tools that we've given the online community sufficient to be able even to reach the native? And so what we did with Foldit is we released a bunch of what we called Quest to the Native puzzles, where we give them the native as a guide, and we give them a Rosetta at home prediction, which is here in green, and the native as a guide here in gray. And just to see, given the tools in this video game, are you able to get to the native? And so these are the results from the first Quest to the native. And so again, this is Rosetta energy versus the distance to the native. And so the first thing you'll notice, which is interesting, is the starting point here is in red, and green are all the Foldit predictions. And you'll notice that a lot of people didn't even bother trying to get to the native. They just wanted to get a high score. And so that's one of the trade-offs that you have with an online game, is people want a high score. And so so that was interesting. But luckily, the highest scoring Foldit prediction here is actually very, very close to the native. And so we have a superposition here. They started with this red Rosetta prediction here, and the top scoring Foldit one is in green, which is very, very close to the native in blue. This was by user Steve B. He's in the Foldit group Void Crushers. Their motto is "Popping Purple Balloons" since 2008. The reason for that is our voids used to be purple, but then we realized that purple is kind of too nice a color. Red means something's wrong. So we have red clashes, and since voids are a problem, we had to change the color to red. So, but they didn't change their motto. Hopefully that's all right. So for Quest of the Native 2, also interestingly, a lot of people just went for a high score without even trying to go near the native. And interestingly, some people even went away from the native and try to get a high score that way. But again, luckily, the highest scoring Foldit solution here was in fact the closest. Yeah.
I was wondering if we could take some questions from the audience.
Oh, yeah, right now, sure.
Do you guys have questions? Or do you need more relevance to why this is important? Like can we bring it together? Can we, like, why do we need to do this? Like, what is going to make these guys want to play your game?
Well, they can cure diseases. Thank you, Chris.
It's okay. You don't need to rush. This is awesome.
Okay.
Just take your time.
Okay. All right. Yes. So, so being able to understand how a protein folds is essential. So the sequence of a protein, the three-dimensional structure of a protein is completely determined by its sequence. So if we can successfully go from the sequence to the structure, then we can in turn understand the function. And the function is everything that's important in a protein. It's if you can understand what is causing a cancer, that's because of mutations in a certain protein. And for HIV, if we can develop a vaccine, that's going to be based on the structure of a protein as well. So being able to determine how a protein folds is exactly what we're trying to do. And so by playing these games, what the Foldit players are doing is they're helping us develop better tools to solve this problem. Okay. But they're learning. I think the Foldit players are learning. This is an example where they started with this Rosetta model that we gave them in red, and the closer that they got to actually going to the native, the better their score got. So this was really exciting, and this was by the Foldit player GS from the Foldit group. Another hour, another point, which I think is a really cool group name because it means that they're playing really, really hard. And that's their group motto. I'll let you read that. Yeah. So anyway, this is just the last example of a Question Native I want to show you, just because they started with this red, very, very loopy Rosetta prediction that, and they're trying to get to this blue one. And this is very, very difficult. And it was quite amazing that, first of all, someone was able to get it, even with the native as a guide, but that they were actually able to get it so perfectly here. This was very, very exciting in terms of our research. And so what this showed us was that the tools actually do exist in Foldit for players to be able to reach the native state. And so this is exciting. That means that the Foldit players have all the tools that they need to become expert protein folders. But so then the next question is, well, what about if you don't give them the answer? How do they do on their own? Which is the more important question, of course. And so actually, we used Foldit for CASP-8, which was last summer, and they actually did remarkably well. In each of these are different CASP targets, and so these are proteins that have not yet been solved, and at the time are completely blind, and then we see the results afterwards. And you can see this Foldit prediction here by the group Another Hour, Another Point, ranked third among all the predictions of all the labs across the world. This one ranked second. These ones did really well. This one even ranked first here. And so this was exciting. But what was even more promising, at least to me, was the fact that Foldit was actually launched in May 2008 of last year, which was the same week that CASP-8 started. And so as the Foldit players were even just learning about proteins at all and learning this game and how it works, CASP was actually going on. And so all these targets were actually very, very close to the end of CASP. And yet they did so well. So it was cool when we posted these results on the Foldit website. The players were all very, very excited. They're like, wow, okay, well now I know a lot more about proteins than I did, when CASP started. When's the next CASP? Like we're totally ready. So sadly they have to wait until next summer for CASP 9. But I just wanted to show a few examples of of proteins where we don't give them the solution. So this puzzle here is a folded puzzle in red, and this is where they start. And you can see the top ranked folded player. They actually got a little closer to the native here in blue. Their prediction is in green, but unfortunately they didn't get close enough. But actually, the ninth top folded solution by this player Vertex from the Richard Dawkins Foundation group did get, in fact, very, very close. And you can see that the yellow is quite close to the blue. So even in cases where they have no idea what the native looks like, they can do very well. And the final example that I'll show is this nice case where basically as the scores got better and better, they got closer and closer to the native structure. And this is a very, very difficult protein to solve because this red one here is all crazy, and the native correct solution here is in blue. And you can see that this solution here by, again, the group Void Crushers was quite close to the native, even though this region here is very different. So,
Ross, sorry, I have another question for you.
Uh-huh.
Why can't you do this yourself? Why do you need people playing video games to do this?
So one of the things that is great about people and humans is that we have puzzle solving skills and pattern recognition, and we can tell that sometimes your score has to get a lot worse for it to get better. And so, a robot with an altimeter and a walkie-talkie is just going to be looking around for a crater, and when it finds a crater, it's going to be like, sweet, lowest crater, I'm awesome. And it's not going to be able to get out of it. Humans will be able to understand, especially with puzzle solving skills, that, if this needs to fit this way, but the only way I can do that is to do this very, very big, complicated move that's going to make my score horrible. And so that's one of the main things. And also just the online community of Enfolded. Players are in groups, and so they share solutions among one another. It's also very competitive, so the groups, kind of try to get higher scores than the other groups. So that's another motivation. And also just sampling. We learned from Rosetta at home that the more and more different trajectories and simulations that we have, the better we can do. And so, I think those are the main.
How much time has this saved you? I mean, if you had to crunch this stuff yourself versus
we've actually wanted to do that calculation. We haven't done it yet, but
does it need to be a video game, the computation itself, or?
Maybe a 3D printing.
But is it a substantial amount of time?
No, definitely. Yeah.
Not to throw you off. I'm sorry.
No. This is great. Yeah. If anybody has questions, please just go like this.
Do we have mics?
Yes. Shout. I'll repeat it.
Okay. So what I'm wondering is, I know there's social scientists that are using video games to help, create peace-making scenarios on war zones or those kinds of things. Where do you see the future of this going? Is this like a holodeck in the future where we solve problems together and run simulations? Where does this go in your brain? Where do you see it?
Yeah. I mean, I think that's exactly it. That is what we're going towards. And I think the important aspect is the group aspect. I don't think this would be successful as a single player, first person folder type game. Like that wouldn't work. I think, definitely. Yes?
So how long does a game of Folded take? I mean, how many people are playing it, and how long does it take them to do one protein?
So we usually post a puzzle for about a week, and that's just because, first of all, we don't want them to get too sick of it. If you're staring at it's one of the hardest thing about this video game is to try to kind of sell it and have awesome graphics and have explosions and stuff. I mean, proteins are proteins. You can't really make them that much better, right? And so we don't want people staring at the exact same protein for too long, or else they get bored. And I think your second question, I think we have about 3,000 users that play. I mean, we have over 10,000 actual users, but that actually play consistently. I'd say about 3,000. Yeah. So that's
Repeat the question.
Yeah. So how much of a background in chemistry or biochemistry do you have to compete in the game? So that's one of the amazing things is you don't. We have intro levels and tutorials, which I showed you at the beginning, and those kind of teach you the basics. But what we've learned is that the puzzle solving skills that gamers have are what's amazing. We actually flew some of the top Foldit players out to the lab at UW and just sat and just watched them play. We give them proteins like, let's see how you fold. And we had the whole department watching, and we're just like, what are they doing? Because they would just take a strand and just rotate it and twist it, and we're like, this is crazy. Like, we would never do this. And then eventually they would get the correct topology because and so we were talking to them like, why were you doing that? Oh, well, I figured this big looking side chain needed to go kind of in the middle, and that's exactly what we want them to do, bury hydrophobics. But they'd figured it out just by playing and by just using the Rosetta energy function, because any move that you make is going to change that score. And so they had figured out, big things go in, score goes up, and so it was really, really cool. Yes.
Is there a case? Can you cite an example where results of the game have translated to, well, solving the protein things, but actually doing something like curing a disease or helping build a drug or?
So we've just started actually Foldit protein design, where we actually give them the tools to mutate side chains and change residues and rebuild active sites and ligands. And we have a group in the lab working on HIV vaccines and are releasing puzzles specifically for that purpose. So we don't have any actual results yet, but we actually are almost synthesizing proteins that have been developed by Foldit players. But I mean, this was just released literally like a few months ago. So this is like brand new. And I'll talk about one aspect of that in a second. Okay, yeah?
You might have already mentioned this at the beginning. Was there an a moment by somebody in your lab that went, wait, this could become a game? Well, it's a puzzle, not a game, but it's a solvable puzzle. And another a brief comment that it seems like the success of this game is because of the inherent built-in competitive nature. That you're leveraging the competitive nature of the game players, of the people.
We are using that to our advantage, yes. No, that's a very, very fair point. Actually, I can tell you a story about the development of the game many years ago. So Rosetta, all the developers of Rosetta, anyone who contributes to the Rosetta algorithm goes to this meeting, actually 2.5 hours east of here in Leavenworth. It's called RosettaCon. And it's a great meeting. We have all these science talks, and then we have hot tubbing and drinks, and it's just really, really, really good. And after probably the drinks.
Did you say hot tubbing?
I hope my professor doesn't see this. Yes, no. And so after either the hot tubbing or the drinks, someone had presented this just really, really basic visualization thing where it was actually for protein docking, where you have two proteins and you just try to dock to get the optimal energy. And he had just this really simple video of, in real time with his mouse, he was just moving one protein and the Rosetta score was changing in real time. And everybody's just like, wow, you can do that in real time? That's just amazing, because usually we'd have to run a simulation, wait for it to come out, and then there would be a score. And so, we're drinking, we're swimming, and someone's just like, dude, what if this was like a PlayStation game? Like, what if we had like, kids like all over the world just docking proteins, and like, that would just be awesome. And I think it just kind of just sat there in the things that get said. And then just, no, it was the Rosetta at Home users that said, I'm watching your screensaver and it's doing things wrong. Let me participate. Let me intervene. Give me the tools to do that. And so that's how actually Foldit got developed. But no, there was a thought about it a few years ago. So yeah, I mean, Foldit players are helping us develop better algorithms. We get a lot more useful feedback from Foldit players than we do from Rosetta. We get feedback all the time like, oh, we need this tool. I need to be able to do this. You need to implement this tool. Sometimes the feedback isn't quite as useful, How do I know that folding won't create a bioweapon? Sometimes we have to reassure players that that won't be the case. But we have just a really great community. We have players, we have groups. There's a Skeptic's Guide to the Universe is one of the groups. And we have, I guess, the old school message boards, but we have a chat as well, and a wiki. And just because it is a video game, they get so into it. Like, it's really cool. But so one of the design puzzles that I was talking about, we kind of let them kind of do what they want with the puzzle, and just to see what they would do. And they came up with these solutions that we had never even possibly imagined. And so this made other players really, really mad because other ones were getting higher scores by doing these crazy things. So this person posted, "Holy cow, Dr. Frankenstein didn't create anything as gruesome as I see here. You know, I vote for trashing this puzzle," and all the scores attached to it. So then there was like a bunch of posts after this, like, "No, I spent all this time on this puzzle. This is like really important. Don't throw away my score." So, but it's really, really great to see the passion that all these players have.
Just the players?
Well, we have passion too. And just lastly, I just wanted to, don't read this whole email, but this is a grandmother with a high school education, and she emailed us, "A funny thing has happened. Over the course of close to a year, I've been playing and I've been learning, probably by osmosis. I'm not pretending I'll ever have enough knowledge to even understand a class in biochemistry, but I can follow some of the conversation, and I'm slowly beginning to comprehend what all this is about." And she ends with, "I know your focus is the protein folding, but I just wanted to tell you that some of us are gaining in ways we never thought possible, and probably you had never envisioned at the start of this project." So when you get these emails, it's just like, this makes you feel awesome. And so I need to thank the entire structure prediction team, the Foldit team, which is amazing, all the Rosetta at Home users, of course, all the Foldit users, and I always like to end my talks with some hardcore profanity, so I'm sure you're all aware of the song "I'm on a Boat," and one of our undergrads in the Foldit team, Alex, he rewrote the entire song about "I'm folding proteins," and this is my favorite part right here. But yeah, anyway, so you can read that while I'm.
You're not going to do it?
Yeah. It's if you go to the Foldit chat, he has a whole bit about that. Yeah. So, okay. Well, great. While you're laughing, if you have some questions.
Given some of the discussions we've had earlier today about competing for attention with the rest of the world, how have you gone about undermining the projects like SETI at Home and the Stardust Project to get attention on yours?
Oh man, I was hoping that question wouldn't come up. Yeah. Okay, so the problem actually isn't just SETI. There's actually another program called Folding at Home, which I don't know if that's where your question is aimed at, but they do molecular dynamic simulations of protein folding, whereas we do predictions. And so, yeah, that's a very, very tough question. But they don't have a video game. Can I answer it with that? Any other questions?
Where was the video game? Did you create that in-house or with a different group on campus?
Right. So yeah, the video game is a collaboration with the Department of Computer Science and Engineering at UW, and actually a postdoc that is now at Carnegie Mellon University. And so we have weekly meetings with everybody in the group. And yes?
When is the iPhone version coming?
Yeah, no. So of course we all have iPhones, and we're all like, oh man, we need to do folded. But there are so many tools already that you have to use a mouse and shift click and alt click, and we've thought about it, but it'd be really. Actually, in my old lab when I was a grad student, we wanted to use the Wiimote to manipulate proteins because. You get kind of a feel for it, or using a haptic device. in robotics would be nice. But yeah. Other questions?
Good. Think we're good?
Thank you.